Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but still want to be its friend.
Aww, it's true. I'm Corinne Caputo. I'm a friend to the universe, speaking of friends, and a friend to our co-host, my co-host.
Hi, that's me. I'm Dr. Moiya McTier. I'm an astrophysicist and a folklorist and a friend to the universe. The universe and I sometimes gossip about our dating lives. I have much less to gossip about lately than the universe does.
You're always seeing someone new.
Always. I mean, there are so many options for the universe.
Can't blame them.
But that is why I've decided to record today in a fire station. I think it would be fun. I think that I would like to meet a hot firefighter.
Oh, yeah.
And I think that there are a lot of ladders in this building, and that is thematically appropriate given what we're talking about today.
You're so right. This is the home of ladders, besides, like, Home Depot.
Right. And I don't feel like going to Home Depot just yet. Maybe in a future episode where I'm doing some home renovations, but not yet.
Yeah.
So we are in this fire station to talk about the cosmic distance ladder. Corinne, does that mean anything to you?
I think no, but what I think this means is like just how far away things are.
Yes.
Okay.
Exactly.
Okay.
This is the name given to the sequence of methods that astronomers have come up with to measure distances in space, because the methods that we use for close objects wouldn't work for really distant objects and vice versa. So we have to come up with this series of things that overlap so we can test their accuracy and go out to really far distances so we can eventually see like the large scale structure of the universe.
Yeah, cool.
Yeah. I wanted to find some history about people's perceptions of like how dimensional space is, because I do know that there were some cultures who saw the sky as like a flat sheet with holes poking through it. Ooh. So like all of the stars were the same distance from us.
Yeah.
But I couldn't find more details about when that definitively came to an end. But it probably would have been very early on. I think that if you're looking up at space and paying attention, you can see that like the moon kind of gets closer and further. You know, like if you have like we have supermoons, right?
Yeah.
I think you can see comets coming towards and away from us. So I think that you would understand fairly quickly that space is three-dimensional.
Yeah.
But then figuring out how to calculate those distances is another thing altogether. And it's kind of based on a very simple concept that we'll talk about. But a lot of it depends on us knowing how far away the Earth is from the sun. That distance is called the astronomical unit. And would you like to guess when we measured that distance?
I'm going to say like the 1500s.
Okay. You have a lot of faith in us.
I am hoping it was the 1970s.
Oh, ye of little faith.
Yeah.
So we I think found at least a close enough real answer in 1672. Before that, we knew how far apart things in the solar system were in relative terms. So like if the distance between the Earth and the sun is 1, then we knew that the distance between Venus and the sun was like 0.7. So we knew everything in relative terms, but we didn't know what the absolute value of that 1 was. So people came up with some different methods. In 1672, Jean Richer and Giovanni Domenico Cassini, for whom the Cassini spacecraft was named, measured the parallax of Mars at 2 different locations on Earth. And from that, they deduced that the sun and the Earth are 140 million kilometers away from each other.
Okay.
The actual value is about 150 million kilometers. So they were very close.
Yeah, that is pretty close.
Very close. They got basically the right answer about a century later, in 1761. And that's because in 1716, Edmund Halley of Halley's Comet fame came up with a way to use parallax during the transit of Venus to measure the distance, except there wasn't another transit of Venus until after he died. I think he died in the 1740s, and then there was a transit of Venus in 1761, and scientists who read his work measured the distance between the Earth and the Sun to be about 153 million kilometers, so very, very close.
Yeah, nice job.
I keep saying this word parallax.
Parallax, yeah. So I know parallax from like design, like internet web page design. It's like the term they use for when like one of the like a background image is moving at a different rate than the image closest to you. So it just creates this effect of distance, but it's just like differently timed mods. You'll see it a lot. Like I feel like Squarespace websites have it a lot. It's just like I don't know how simple it is from like a coding standpoint, but it seems to be this mod that like gives a big impact with like just less of a lift from the dev team. But it's about just like the movement of things that are closer and further away from you. So I'm assuming it's the same thing of like something far away has a different, to the human eye or from wherever you're looking at it. Yeah. Just moves differently.
Yes, that's perfect. That is exactly what parallax is. It has to do with how much objects appear to move from our point of view when they are different distances from us. So this is something that ancient Greeks first used and like first recorded, at least. And this is something that they would have observed in their everyday lives. This is something that everyone listening to this right now has observed in their life. And if you haven't, I'm going to make you experience it right now. So hold out your thumb like an arm's length away from you and close first one eye and see where your thumb is compared to some object in the background. And then close the other eye, like switch eyes.
Oh, yeah.
What happens, Corinne?
Well, I have one of our Google Docs open right now, and in one eye, I'm covering my profile photo, and in the other, I'm not.
Yes. When you switch eyes, you are switching your point of perspective, and the distance between your eyes is enough that it can actually make it look like your thumb has moved relative to the background, but it's not. Your point of perspective has just shifted. Distant objects have smaller parallaxes. They are going to appear to move less as your point of perspective shifts than an object that's closer. Yeah. So this is a method that we can use to measure distances in space, but only for pretty close by objects, because if you get too far away, their parallax is really small.
Sure.
And even when we're just using our eyes, even like a very close object has too small of a parallax to see. So this goes back to 130 BCE when the astronomer Hipparchus couldn't measure any parallax from the sun because it's too far away from us to see any parallax without the aid of a telescope.
Ooh, okay.
So he couldn't find any parallax measurement, and that led to uncertainty in Hipparchus's measurement of the Earth-Moon distance, but he did set the non-existent parallax of the sun to be some like maximum level. Like the sun is the farthest thing away you can measure parallax for. But that's because he could only use the Earth as his shift in perspective. Like the furthest, and he never did this, but the furthest away he could get was the opposite side of the Earth, right? So that's what, 8,000 miles of a difference in your point of perspective.
Sure.
In order to see the parallax of stars, or like distant objects, you need a much larger baseline for your perspective shift. So what we do today is measure the position of a star when we're on one side of the sun, and then we wait 6 months to measure its apparent position all the way on the other side of our orbit. Yeah.
Okay, yeah.
And that gives us a really wide baseline, and it lets us see stars up to like 10 to 15,000 light years away. So not outside of our galaxy, but almost to the center of our galaxy.
Yeah.
Yeah, parallax is really powerful. It's I love how intuitive it is as a method. Like we can all do that thing with our thumbs, and it's good for close-in objects, which is where we found all the planets. So that's something that's close to my heart. It also gave us a new unit. Do you remember hearing me talk about parsecs before?
Yes, for distance. For
distance.
Yeah.
Yes. There's that whole Star Wars thing about people using it as like a unit of time.
Yes.
But it is a unit of distance, and a parsec is actually a portmanteau of two words. So the parsec is the distance at which an object's parallax is 1 arcsecond. So if an object is 1 parsec away from us, its parallax from like one side of our orbit to the other is 1 arcsecond, which is 1/3600th of a degree.
Small.
It's very small.
Okay.
1 parsec is about like 3.5 light years.
Okay.
And like I said, it doesn't really work for other galaxies, which means we have to move up to the next rung in the distance ladder for those objects. But do you have any questions about parallax?
I think I get it. I think you're right that it feels intuitive, and that makes me feel like I understand.
Good. That makes me feel like I've done my job. Okay, so the next rung on the distance ladder is standard candles. Does that mean anything?
Candles is also like a unit of measuring something, but not distance. Like, is that right?
Yeah, I think there's like some unit of brightness that's candles or like lumens or something. But the standard candle is a class of object. Mm-hmm. It operates on the principle that if we know how bright an object is, like intrinsically, and we know how bright it looks to us, then we can calculate how far away it is because we know how brightness falls off with distance. We know that there's an equation. The brightness decreases with the distance squared. So if something is 3 times far away, then it's 9 times dimmer because it's 3 squared.
Okay.
So standard candles are objects that have a standard brightness. We know how bright they are intrinsically, and then we measure how bright they look to us, and then we do that distance calculation.
Okay, cool, yeah.
Yeah, there are a few types of objects that are like this. I'm wondering if you had to guess what type of object might be a standard candle, something that is always the same brightness.
I feel like stars will fade. So I don't know if it is a standard candle. Yeah,
stars do fade. Some of them get brighter, but their brightness can change over time. But there is a very special type of star called a Cepheid variable, which we mentioned briefly in the last episode. They were studied by Henrietta Swan-Leavitt, another woman who worked for Edward Pickering, and they pulse. They pulse in both size and brightness, and they do that periodically. A lot of people use periodically to just mean like sometimes, but it means with a regular period. So like we can rely on the periodicity of these Cepheid variable stars. And when Henrietta Swan-Leavitt studied them, she found that there's a relationship between the period of the pulse and how bright the Cepheid variable star is. So the brighter the star is, the longer you have to wait between its pulses.
Okay.
Which means when we look out at one of these Cepheid variable stars, we can measure its period, and that tells us how bright it is at the peak of its brightness, and then we can do our distance calculation on that. And that's a really good distance measurement.
Yeah.
And we can definitely see these on the edge of the Milky Way galaxy, and I think we can see these in some of the galaxies in the local group, but probably not too far beyond that. If we want to go further out, we can still use a standard candle, but it has to be a different type of standard candle, and it's actually going to be a type of supernova. I think we did an episode. What episode was it? We did a whole episode about supernovae, but I don't remember which one it was. But in it, we talked about the different types of supernovae, and some of them form when a really massive star stops fusing in its core, but some of them form through different processes, and that's the one that we're interested in. So we are interested in type 1a supernovae. Do you remember me talking about those?
Yeah, it's ringing a bell.
This is the type of supernova that forms from 2 stars orbiting each other. So if you have 2 stars orbiting, and one of those stars is a white dwarf, which means it was a star like our sun that burned through all of its fuel, and now it's just like a chunk of hot rock in space. If one of the stars is a white dwarf, it can actually gather material from the other star that is orbiting with it. And if it gathers enough material to cross a mass threshold of 1.4 times the mass of the sun, then it will implode as a supernova. And because it happens at that specific mass threshold, all of the type 1a supernovae are the same brightness and their light curves are the same shape. So we can use that as a standard candle, which is really exciting.
Okay, yeah.
And they're so bright that we can definitely use them in other galaxies. And this and Cepheid variables were two of the methods that Edwin Hubble used when he was like studying the expansion of the universe, because he was looking at really distant galaxies and their variable stars and their supernovae to measure how far away they were.
Yeah.
Yeah, I said that this rung takes us out to other galaxies. If you're specifically talking about type 1a supernovae, they can measure distances of 1 billion light years.
Wow,
So really,
very far.
Really far. Hi friends, Dr. Moiya here. Corinne went to go pet the station house dog, so I figured now would be a good time to give you some messages and thank our patrons. I'll start with that. Thank you so much to our sun-like stars, Scott Reynolds, Augustin, and Tom T. You are golden, and you have the perfect mass, just holding everything in place around you. The rest of the solar system owes you all our gratitude. If you want to join this amazing club of our patrons and get to hear your name on the show and make your mark on our patron star chart and get research notes for every single episode, except for some of the movie episodes, if I'm being honest, then you can support us on Patreon for just about $1 per episode. And we also offer annual memberships. So if you sign up for a whole year up front, you end up getting a 13% discount across the entire year. That's 1 percentage point for every constellation in the sun's path in the sky. You can find our star chart, our Patreon info, and more at our website, palebluepod.com, or you can go right to patreon.com/palebluepod if you already know you want to support us financially. Of course, if that's not a real option for you right now, that's totally fine. We love you, and you are very much still space. There are other ways that you can support us and help the show grow, and we really hope that that's something you want to do. You can rate and review the show on whatever app you use. I personally love reading all of the comments that we get. And you can share the show with your friends by taking an episode that you think someone in your life would like and digitally sending them the link. That is a great way to help our show grow, and we would really, really appreciate it. Okay, now I have a message, and it's coming from the Multitude Collective. Did you know that we are in the Multicrew Drive? We are trying to add 100 new and upgrading members to Multitude's membership program called the Multicrew by September 27th. That's this week, folks. Because your support sustains our business, it fuels our growth, and it just makes our hearts feel warm and fuzzy. We're doing 3 cool new things during the drive to thank all of our members. First, all members of the Multicrew will get an adorable enamel pin that says support homegrown podcasts, because by supporting the Multicrew, that's what you're doing. You are supporting indie podcasts. And that goes to all members of the Multicrew because we love you all. Second, everyone on an annual plan will have their name inscribed in the "This Certifies We're the Best" crest. Annual plans help us plan for the future and give you 2 months free on your membership, by the way, so it's a win-win, just like how here at Pale Blue Pod we offer an annual membership. The Multicrew does the same. I actually got the idea from them. And the third thing we're offering is that you will get 6 exclusive, standalone, brand new podcast episodes to celebrate this year's Multicrew Drive. We've already dropped 4, and there are more coming this week. I did an episode with our editor, Misha Stanton, called Deep Blue Pod. This is something that Misha's been wanting to do for a while, and they finally got to do it for the Multicrew Drive, where they gathered a bunch of cool ocean facts and taught me stuff about the deep blue ocean here on Earth. And it was really fun. And so if you join the Multicrew, then you would get to listen to it. To join the multi-crew, you have to go to multicrew.club or the link in this show's notes and join by September 27th of 2024. That is this week, so do not delay. You can get your free pin, you can have your name inscribed on our wall for annual members, and you can help us reach our goal of 100 new and upgrading members. All of that will support the work that we do here at Multitude. So there's only a little bit of time left. Go to multicrew.club to join the multi-crew, and you'll get some really cool perks. All right, before we get back to the episode, I just want to let you know that the other podcast that I've been hosting for 4.5 years, called Exolore, all about facts-based fictional world building, is now complete. I did 100 episodes plus one bonus stats episode talking about the guests and the types of episodes that I did over 4.5 years. But there are 100 substantive episodes for you to listen to where you can be introduced to brand new fictional worlds that I built with guests from scratch. You can dive into existing fictional worlds and hear me break them down and analyze them for, do their rules make sense? And do I think that this is a well-built world? You can also listen to me interview world builders and experts to learn their tips and tricks. I had so much fun making this podcast, but life goes on. I grow up. I started making Pale Blue Pod, and now I want to focus more energy on that. So yeah, my other show, Exolore, a show about facts-based fictional world building, is now complete, and you can go listen to the 101 episodes that exist of it wherever you get your podcasts by searching for Exolore, EXOLORE, wherever you get your podcasts. It was a really fun ride, and I would love it if you went and listened to it and shared it, because I'm done with it for now, but I don't want the world to be. So Exolore, wherever you get your podcasts. And Corinne is back. She looks very happy, as anyone would after spending some time with an adorable Dalmatian. But let's get back to this episode. Next, we have something that you're probably not going to see discussed a lot if you are just casually reading about the cosmic distance ladder, as one does. But a lot of people just kind of skip right over this step. It is standard sirens and standard rulers, which operate on kind of the same principle. Standard sirens are for sound. So a gravitational wave source that chirps at a specific frequency would be a standard siren. Does chirping make sense? Do you know what I mean when I say chirp?
Yeah, I think you don't mean oh my gosh, did you see that news report this week that the astronauts were hearing something spooky?
The astronauts that are stuck on the ISS?
Stuck in space.
They hear spooky stuff in spooky season?
I think they were definitely writing a more sensational headline than was the truth, but they were they called down to be hey, are you hearing this? And it took them a while on Earth to hear it. It was this kind of pulsing noise. I don't know how it resolved, but it did sound creepy. So I don't think you mean chirp that, but just that the gravitational wave is predictable, where there's this moment in it at a specific frequency that you can expect.
Yes, it's the specific frequency thing. So gravitational waves are caused by really massive objects orbiting each other and distorting the fabric of space-time as they do that. So you can imagine ripples in the fabric of space-time coming off of this. And those ripples will have a certain wavelength. And they're also really powerful events, so the wavelengths are really short. And when gravitational wave scientists study that data, they kind of speed it up to put it in the range where we can hear it, where we can hear the frequency, and then they call it a chirp. So the frequency of the waves is going to depend on the masses of the objects that are colliding. And so if you know the chirp, if you know the frequency, then kind of like an ambulance, when you can kind of tell how far away an ambulance is by that Doppler effect, we can do something like that with standard sirens.
Okay, cool.
And then standard rulers are, again, a similar concept, but it's based on if you know how big something actually is and you know how big it looks to us than you can measure. And so for this, we have to turn to something that's really large and present throughout the entire universe. And it turns out that there is this signature left over from an event that happened early on in the universe. And that signature is called the Baryonic Acoustic Oscillation, or BAO. So early in the universe, when everything was a lot closer together and the universe was much hotter, there was a pressure wave that moved through all of the material in the early universe. And even though the universe has expanded since, the kind of residue of that pressure wave still exists. We can still see that there are peaks and troughs of density. There are like places where material has bunched up, and we can see it in waves throughout the universe, which is wild to me. We've confirmed that this is true by studying the cosmic microwave background, which is the heat signature left over from the Big Bang. So we know that the BAO is there, and the distance essentially between the peaks of this oscillation are about 360 million light years. Big. So this is useful on scales much larger than that. So we're talking billions of light years. We're going out to other superclusters of galaxies, and you're starting to get into the large-scale structure of the universe when you're talking about the Baryonic Acoustic Oscillation.
Yeah.
Another thing about the BAO is that it is one of my favorite things to say when I'm trying to sound like TV show smart. So if you ever hear me busting out like baryonic acoustic oscillation or hydrostatic equilibrium or like simple harmonic oscillators, I love oscillators anytime I'm trying to sound smart.
Yeah, that is, you know, I never pull out that word when I'm trying to sound smart, but maybe I will.
It works. It really works.
Yeah.
Throwing some harmonics in there.
Yeah. Totally.
Quantum. Just throw in a quantum every once in a while, and people will assume you know what you're talking about.
That's so funny. Well, I feel like I'm never caught talking about science, but maybe I can still find a way to sneak it in.
Corinne, you're the co-host of a science podcast.
I know. I think I don't put myself in a position where I'm like, I'm the authority here.
Hello.
But I should. Maybe I should.
You do know the things. Especially how much things cost and how much things weigh. You're really good at that.
That I love knowing. That I do. You know what I realize I'm good at? And maybe I'm only good at if I've smoked a little weed, but I can guess what year a movie came out.
Oh, that's a great talent.
And I think I need to be looking at the movie poster. That like really helps me place the like time. But Eli and I did that one night where he just kept like randomly going to movies, and I would say a year, and then I'd be right.
Oh, that's good. Do you remember the movie Sky High?
Yes. Oh my God.
I feel like that would be a nice little sidekick superpower.
Wasn't that a Disney Channel original movie?
I don't think so.
Or, oh no, wait, it was with that, Michael Angarano is the main character. He's married to Maya Erskine of Pen 15.
Oh, wow.
Trivia. 2005. This is the year that came out.
Did you look that up, or did you look at the poster?
That one I did look up because I was like, I know this movie.
I really loved that movie. I think that was the first time I saw Stephen Strait, and then I watched was it The Covenant with him in it?
Oh,
he was fine as hell.
Stephen Strait. Haven't thought about him. Yeah, The Covenant.
Yeah. I don't know anything about him as a person, so don't come for me.
Don't come for me. Face only.
Face only.
Ready.
Yeah. Arms too. Okay, back to science. Are you ready for the final rung in the distance ladder?
Yes.
Fantastic. This is one that we have talked about before. We did a whole episode about redshift at the batting cages. It's episode 17, so go check it out. But on the largest scales of the universe, when we're trying to calculate distances, we are looking at cosmic redshift. We are looking at the way that the universe itself, with dark energy, has expanded, and using that as a proxy for distance. So when, on the largest scales, dark energy expands the universe, it makes the bright things far away move away from us. This shows up in our spectral data as that object being redshifted, so it looks redder than it should. And we can study exactly how much redder it is than it should be. And thanks to a relationship found by Edwin Hubble in the 1920s, we know how to go from the redshift of an object to how far away it is. Because Edwin Hubble was studying standard candles. He was using standard candles to measure distances to faraway galaxies, and he noted that the galaxies that are further away are more redshifted, and they're moving away from us faster. So we now have this relationship called Hubble's law between an object's redshift and its distance from us. And it only works for really, really far things.
Cool. Hubble's law.
Hubble's law. Thanks, Hubble. Also told us that we lived in galaxies.
That's important to know.
Right? Such a revolutionary figure. So that's the distance ladder. That is how astronomers have taken what looks like a two-dimensional smattering of lights in the sky and turned it into a three-dimensional space that we can study, we can map it, we can predict how things are going to move in it, and that's really exciting to me.
I love it. I didn't realize... I love that it's called the ladder. I think it's so cool.
It is. Sometimes astronomers have a sense of humor.
Yeah, I'm in.
Okay, cool. I do have some superlatives for you.
Ooh.
Yes. I'm going to ask you for them, but I won't make you guess multiple times like I did in the last episode. I have 5 of them. Corinne, what do you think is the closest star to us, aside from the sun?
I have heard it before.
You have heard it before.
I don't think this is it, but something with the letter V is coming to me. But I might just be thinking of Venus.
Yeah.
No, that's close.
You know what? That is very close. I'm going to give it to you on the condition that we go back in time and say that I asked for the closest planet. So question number 2, the closest star to us is actually Proxima Centauri.
Oh, I have heard that.
Yeah. Called Proxima because it's most proximate to us. And it's also known as Alpha Centauri C. It's part of a triple star system.
Alpha Centauri. That one is even more familiar to me.
Yes. And I used to always get them confused, or I would interchange them. But Proxima Centauri is actually a very small star, about 12% the mass of the sun, that orbits 13,000 astronomical units away from the rest of the system. The rest of the system is a little binary pair, Alpha Centauri A and B, and they're 25 astronomical units from each other. They're basically touching.
I was going to say, that seems really close.
Really close. And then this third star is outside. And altogether, the system is 4 light years away from us.
That's not that far away.
In the grand scheme of things.
Yeah.
Basically our backyard. They are encroaching on our property.
For sure.
And that would be cruel. So the closest galaxy to us might actually surprise you. Can you name any galaxy close to us?
I don't think I can name another galaxy.
Okay. It's not Andromeda, which is the closest, big spiral galaxy to us. And it's not even the large and small Magellanic Clouds, which are the small satellite galaxies that a lot of people talk about. You can see them with your own eye if you're down in the southern hemisphere. But no, apparently the closest galaxy to us is the Canis Major Dwarf Galaxy, which is 42,000 light years away from us. That's so close.
Canis Major,
so close.
I'm thinking of a constellation. Am I just combining constellations?
It is. It looks like the galaxy is in that constellation.
Oh, okay.
And it's just actively being kind of absorbed by the Milky Way, so it's very close to us.
Yeah.
Then the most distant actual object from us is a galaxy. It's called JADES-GS-Z13-0. It's a beautiful name.
Oh, yes, that one. Gorgeous name.
I think if I ever have children, I'll probably name them after this, right? It is a long string of numbers and letters that tell us what survey found it and the redshift. So that Z13 tells us that it's at a redshift of about 13. This is the most distant galaxy from us ever discovered by JWST, and it is, so the universe, about 14 billion years old. This object is about 33.6 billion light years away from us. whatever light it's emitting now, we will never see. We are only seeing the light that it emitted early in the universe before it got carried away by dark energy.
Okay.
Isn't that scary?
Yeah, that sounds spooky.
But also, doesn't it just make you feel so connected to this object that you'll never, ever get to touch?
Yeah, I guess.
It's like when your long-distance friend sends you a snail mail letter.
Oh, I do love when that happens.
Yeah, that's how I'm thinking of it. Mm-hmm. Would you like to know what the most isolated object in space is? So we can feel bad for it.
Yeah. Aw.
This is the object that is furthest away from anything else in space, as far as we can tell. It sits in a void, so this big empty space between clusters of galaxies. The nearest galaxy to it is 100 million light years away.
Aw, it's so lonely.
It's so lonely. For reference, the Andromeda Galaxy, which is not very close to us and is the biggest closest spiral nearby, is 2.5 million light years away from us. So
far.
This galaxy is super isolated, and it's called MCG plus 01 minus 02 minus 015, which is probably like the date it was discovered or something, or its position in the sky. It's probably position in the sky.
Sounds like a document, like what would be like auto-generated for like when you save a new file, if you don't like rename it.
Yes. Oh, that's so true. I talk about this galaxy in my book. Actually, I talk about the whole distance ladder in my book, the Milky Way, and I heavily referenced it to prep for this episode. But the Milky Way galaxy in my book calls this galaxy Macy, and all of the galaxies feel bad for it, but also kind of talk about in whispers, like, what happened to make it go so far away.
Yeah, like totally kicked out of the group.
Mm-hmm. And then, finally, the most distant object we can see without help of a telescope, if you have good eyesight.
Okay.
I've heard a lot of people say it's the Andromeda Galaxy, but at least according to one source that I read, that's not true.
Okay.
It is actually... Oh, wait. No, it must still be the Andromeda Galaxy. Never mind.
Good.
I forgot that 16,000 is less than 2 million. It's fine. It's fine.
They're both big numbers.
So the most distant object you can see without help of a telescope is the Andromeda Galaxy. It's 2.5 million light years away. It holds about 1 trillion stars, between like hundreds of billions and 1 trillion stars. Mm-hmm. And it's just like a little bit less massive than the Milky Way, but they're still close. And they're on a collision course for each other. In like 5 billion years, we're going to be merging with Andromeda. So it's always getting closer, which means that now is the time when it's the furthest away that you will ever see it.
And tomorrow it'll be closer. Mm-hmm. Aww.
Yeah. That's the superlatives for distance.
Love it. Love the yearbook.
Yeah, like closest or biggest or anything. But you could ask me, but I wouldn't know off the top of my head.
I think the distance is appropriate. The closest and furthest.
Okay. I would like to know a little bit more about your personal distance ladder, Corinne.
Yes. Okay.
Yeah.
What is that?
So I don't even know if we can call it a game, but I would like to know what you would consider too far in different scenarios.
Ooh, okay.
So Corinne, how far is too far to walk?
Ooh.
Say like someone invites you somewhere.
Yeah. I love walking, so I feel like my threshold is pretty high. But if I was invited to like a party or something, I feel like the most I would walk there is like 45 minutes.
Okay, so like 2 miles.
Only because I want to like look good when I get there. I don't want to like put a whole workout in, but I would walk home further than that. I would spend like 3 miles home.
Wow. Like an hour.
This isn't what I would like love do. Like this isn't a dream. But I oh my gosh, I did that all the time in New York. We'd just like leave something and be like, should we just walk home? And we did, and I missed that quite a bit.
Yeah. Okay, good to know. I think mine is much shorter. Like in New York City, I will walk 20 blocks.
Yeah.
But if it's further than that, I'll probably get on a bus.
That's a good idea.
Yeah.
That's what I would do for, like, it depends how leisurely I get to be that day.
That too. Okay, but about 2 miles. That's Yeah, 2 to 3 miles. Okay. How far, and I know you don't drive.
Yeah.
But how far is too far for a car ride?
I really don't like car rides. I think it would depend how long I'm spending at the end spot.
Okay.
Like, I commute to Boston for work, so it's 2 hours each way. So that's my max.
Interesting. That, I'm sure that this varies so drastically for people in the U.S. Like, people in Texas.
Oh my gosh, you're driving for
number.
hours
Yeah.
just to get to another part of Texas. I guess that's for a day trip, like 2 hours each way. I feel like could be a day trip.
Okay.
But like we'll drive from Maine to New York, but it always takes us like 8 hours, which we don't like doing, and then it feels like we like lost a day. But if I'm spending a lot of time once I get there, it feels less bad.
I agree. Yeah, I've done the 8 hours from New York to Maine several times, but always for like at least a weekend, you know? Like,
there's
about
like
a week.
A treat at the end of it.
Okay, that does take me to my next one, which is if you're going somewhere for a 5-day vacation, that's including travel time.
Okay.
How far is too far to go?
Including travel time. So it's really only 3 full days at our destination.
It could be.
I think the farthest I would go was New York.
For a 5-day vacation, you're not leaving the continent.
Oh, then I would go further. When I went to London last month, and it was, I guess we were there for like 4 full days, but that was like, it felt like a great amount of time. So I would leave the country for that. I think that I would like the flight to be 6 hours would probably be my dream.
Okay. Yeah, I agree. I think I would definitely not go to Australia if I only had 5 days.
No.
I don't think I would go to South Africa. But I think I would go to, like, Northern Africa. I would go to Europe if I had 5 days. So, yeah, probably like 6-7 hours.
Yeah, I think I would set it at 6 or 7 hours and then see how far I can get.
Great. Now I know a little bit more about your distance ladder.
Yeah,
Thank you, Corinne.
My distance ladder.
Anything else we should discuss before I slide down this pole?
I can't wait. This fire station, I hope they invite us for their big family meal.
They better.
I have like a storybook image in my head of like all the firemen making chili together every night. So
I love that. Well, I brought us here so I could find a person. So I'm going to make sure we're invited back to this family dinner.
I'm going to go talk you up to all the guys here.
And the firefighting ladies, too.
And of course the ladies, of course.
Yes. All right. Well, then I think we should pack it up.
Okay, listeners. Gotta go.
All right, yes, we're going to go try on some equipment. Enjoy the rest of your day, hopefully fire-free, friends.
Bye.
Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.